Welcome back, everybody. AP Chemistry, and this is Unit 9, Section 5, taking a look at the solubility equilibrium, or KSP. What we mean by that is after the reaction has achieved equilibrium, what is that value, okay? That's the solubility constant, and it's used to predict the solubility of any of the particular salts. Now, this is kind of a weird one to be putting in with acids and bases and buffers, but remember, those salts can be affecting the pH and pOH of a solution if they dissolve or dissociate into the solution. So that's why I'm introducing it here. So let's take a look at a couple of things, figuring out those KSP values for the following salts. It's all derived by what we end up dissociating into. So the first one I'm going to go slow with. Remember that this is going to be dissociating into one of your strontium ions, okay, and that will be aqueous in solution, plus one of your chromate ions. Okay, and that's going to be aqueous in solution. So if I was going to find and write the expression for, well, my KSP is going to be the concentration of my strontium ion, raised to the 1 power because my coefficient was 1, times my chromate, which is CrO4 to the -2, so that's the 1 power as well. Okay, there's my equation for this. We've done this before, guys. It's not anything all that tricky. It's just bringing back some of those skills from what we've, like I said, done before. So if we take a look at a couple examples, I'm going to speed it up a little bit. We can just envision this. I'm going to get a KSP is going to be 2 of my silvers. So that raises it to the 2nd power times 1 of my chromates. Okay, so that's the 1st power. That's that particular one. Now we take a look at the next one, and you see that it's going to be one more level of this because I'm going to get a KSP is going to be my calcium ion, and that's going to be raised to the 3rd power times my phosphate ion, PO4 -3, raised to the 2nd power, okay? So it's just dissociating those into those ions, and you know how to calculate for your K value. We've done that before. Now, there is a table that I've provided for you that gives you some of these values. So this is a handout. I'm just giving you examples, some of these things. You see we've got fluorides, chlorides, bromides, iodides, sulfates, chromates, hydroxides, all those things, and it just gives you some of the common ones along the way. Okay, so those are just some values that will be given with this, and you can see how we can put this into play. Notice that my KSP is going to equal my copper ion, and notice it's going to be a +1 charge, times the concentration of my bromide ion. Okay, and that's to the +1 or -1 charge. Okay, my KSP value then, if I look at this value, I see I have 2.0 times 10 to the -4. Notice that this will dissociate into those two, so I've got a 1-to-1 ratio. My CuBr is going to break down into Cu plus my Br. Okay, and so I see that I have a 1-to-1-to-1 ratio. So that means if I have 2.0 times 10 to the -4 of this guy, it means that I have 2.0 times 10 to the -4 of this one. Okay, and we're going to multiply that by 2.0 times 10 to the -4 of my bromide. Okay, so my KSP value, if you don't see it on here, I can still calculate it. And so if I just multiply those, my KSP ends up being 4 times 10 to the -8. Remember, we add exponents when we multiply, okay? So that's all we needed to do for that one. If you don't see it on this chart, then I would just go through and do it that way. But let's take a look at how this works when I have a little bit more complex of a reaction. Notice that I have bismuth sulfide, so Bi2S3 is going to dissociate into my bismuth ion. That was a +3, and my sulfide ion, and that was a -2. But be careful, because I've got 2 of those and 3 of these, right? And so I have 1 of these. So if the molarity is going to be 1.0 times 10 to the -15, that means that I have 2.0 on this side. Okay, so this is going to be 2.0 times 10 to the -15, because I doubled it, and I have to triple this guy. Okay, so if I do that, I end up with 3.0 times 10 to the -15. Now remember what I do with this. Okay, if I'm finding my KSP will then be taking into account, I doubled it because it's a 1 to 2 to 3 ratio, and I am going to be squaring this and taking the cube of this. And so my KSP ends up being a value of 4 times 10 to the negative 30 times 2.7 times 10 to negative 44. Okay, and so what I'll get is a KSP value. SP is going to be 1.08 times 10 to the negative 73. Okay, that is my solubility constant for it. Okay, that's just the value that we have for this. All right, so now you see how the effect of those coefficients are going to play in. Okay, and you'll be using your table in there, otherwise I'm given that. Now we can do the opposite of this. If I'm given my KSP, I can figure out the concentration of these, calculate the solubility of the following salts given this type of scenario. Okay, so let's take a look at how I can use this. This is going to be, if I see I've got silver chromate, remember that was Ag2CrO4, is going to dissociate into 2 of my silver ions plus 1 of my chromate. Okay, I like to include the 1 in there just to keep things nice and clean. And so I see I can work this problem backwards. My KSP is going to equal, now remember, I have 2 of these, and so my concentration is going to be 2x squared times x. And this is going to be raised to the first power, isn't it? Okay, there's my silver, there's my chromate. Okay, so this is equal to the 9 times 10 to the negative 12. So what do I have in here? 2x squared is 2x to the second power is going to be 4x squared times x. So this means that I have 9.0 times 10 to the negative 12 equals 4x cubed. And so I take the cube root. X is then going to be 1.3 times 10 to the negative 4. Okay, that is going to be the solubility of that salt. Okay, 1.3 times 10 to the negative 4. And that's all I need to do. Write out your balanced equation, and so you can see how many is there. Now, we're going to be adding in that value, and we're going to be adding in a little bit more of my silver. So it's going to dissociate into silver, but I'm going to be adding in some silver as well. Okay, so remember what we did. What we did was we took a look, first of all, at my solubility. We had the Ag2CrO4 is going to dissociate into 2 of my silvers plus 1 of my chromate. Okay, but we're also adding in some silver nitrate. And so that's going to dissociate, and I'm going to be adding in 1 more of my silver, and I'm going to be getting in some of my nitrate with this. Okay, so we knew that the KSP on this one, just to kind of follow this one, let's do this one up here. We saw that we had, in this case, my KSP was equal to my silver ion, and I have 1 of those. I'm following the nitrate, and I have my nitrate here. Okay, and there's 1 of those. So my KSP for this scenario is going to be 0.1 times to the first power times 0.1 to the first power, because it's a 1 to 1 to 1 ratio. And so my KSP for this one ends up being a 0.01. Okay, so what we had at the to kind of sum all of this up, well, I had my chromate. Okay, remember this guy was going to be let's see, the 2x squared times my x to the first power. Okay, and we did have that my value we calculated out to be let's see, 9.0 times 10 to the negative 12. Okay, so when I see all of this, what do I need to do? Well, I need to combine all of these things together. Okay, if I saw we had the 9 times 10 to the negative 12 that was provided before, remember my 9.0 times 10 to the negative 12, that's going to equal now. Again, combining these two together, I saw I had 2x, and I'm going to be adding in the 0.1. Okay, so I added in the silver. Okay, we don't really care about the nitrate. He doesn't do anything. Now I also had the chromate, because that's going to be the solubility of this with that. So I do have to include my my chromate in there, and that was my X. Okay. Now 2x, this is a very small number. So if I double that, it's still a really small number. So what do I really end up with? I end up with 9.0 times 10 to the negative 12 is going to equal 0.01x. Remember, I squared this. So 0.1 times 0.1 is 0.01. My x ends up being 9 times 10 to the negative 10 now. Okay, so what I did is I followed this one, and I saw, oh, I'm going to be adding in 0.1 with all of this. Okay, and that 0.1 came from my molarity. All right, so that's how we do that when we add in a little bit more to our solution. Okay, adding in a little bit more silver. Now, let's take a look and do the same thing with calcium fluoride, and I think you're going to see how this all works. You can see we're going to be doing the exact same scenario in just a moment. Okay, so my calcium fluoride we saw was calcium fluoride is going to dissociate into the calcium ion. There's one of those for every 2 of the fluoride ions. Okay, those are going to be aqueous along the way. So if I take a look at my constant, is 4.0 times 10 to the negative 11. And so that will equal my calcium ion concentration to the first power times my fluoride ion concentration. And there's 2 of them because it is a 1 to 1 to 2. And so that's going to be 2 of my fluorides to the second power. Okay, so that will equal then 4 times 10 to the negative 11 is going to equal x, okay, to the first power, times 2x squared. That's my fluoride, okay? And so this will equal 4x squared, and so that'd be 4x cubed. And I can solve it that way. 4x cubed, my x ends up being 2.15 times 10 to the negative 4. I divide both sides by 4, and then I take the cube root. So 2.15 times 10 to the negative 4 is my KSP. Okay, so that's finding for my calcium fluoride. Okay, so now let's do the next step that we did previously. And the reason we're doing this is because now you see that 2 will play a factor. Okay, we started with the calcium fluoride in the first place. Now notice I'm going to be adding sodium fluoride, but who cares? It's really the fluoride that's going to be added to this process. Okay, so let's just go back and remind ourselves what we had. We saw that we had the KSP originally with my calcium fluoride. That was going to be 4.0 times 10 to the negative 11. That was equal to x. This was my calcium. Times 2x squared, that was my fluoride. Okay, so that was when I had calcium fluoride. Now we're going to be adding in we're going to be adding in sodium fluoride. Now sodium fluoride is going to dissociate into 1 sodium, and let's see, and it's going to be making 1 fluoride. Okay, so there's 1 and 1. So you see what we're doing with my KSP? I started combining the 2, didn't I? My KSP is going to be sodium ion to the first power times my fluoride to the first power. So that's going to be, and we also have my value is given. Since this is a 1 to 1 to 1, if I have 0.025 moles of this, it means I have 0.025 moles of this. So it's 0.025 and 0.025. Now, who are we tracking? We're tracking the fluoride. Okay, so my KSP for this one ends up being, let's see, it's going to be 0.025 and 0.025. Okay, again, this is going to be my sodium, and this is going to be my fluoride. Okay, so notice that I can combine all of these terms together. What do I end up with? 4.0 times 10 to the negative 11 equals x times 2x plus the 0.025 that's being added in there squared. This guy is really small, we can disregard, so it's 0.025 squared. And this is just x, and so I end up with 4.0 times 10 to the negative 11 is going to equal, let's see, 0.000625 x to the third power. Okay, so x will end up being 6.4 Nope, I'm sorry, that's not to the third power, that's just x, because this guy's gone. Say 0.00625, that's this squared times x, and so 0.00625 x, so 6.4 times 10 to the negative 8 is going to be my solubility. Okay, so pretty simple math once you just kind of keep your wits about you and follow that. Now, we can use this to do something even more. Okay, we can figure out, predict if something's going to make a precipitate or not when we mix those. And what we're going to do, remember our K is what happens at the end of equilibrium. Okay, but as we're mixing it, this reaction quotient is actually telling us what's going on as the reaction is going. If I find that I'm getting more Q's than K's at the end of equilibrium, then I'm going to get a precipitate. I have more of this, that means stuff is going to fall out of solution. If I find my K value at the end of equilibrium is larger, then it's the precipitate is not going to be forming. I have less at the beginning of it, so it's not going to be there. And then we can find if my Q equals K, that it's completely saturated. So here's what we can do with that. Again, Q is when the reaction is going, and K is at the end of things. So I'm going to be mixing these things together. We're going to be mixing them in a solution of my strontium, and I'm going to be mixing it with the sodium chromate. Okay, so the question is, when these form a reaction, what am I going to get? I'm going to end up with strontium chromate. Okay, it's going to kick that sodium out as a spectator ion, and so my sodium chromate is going to be a dissociation of strontium ions as well as my chromate ions. Now notice it's a 1 to 1 to 1 ratio. Okay, and so if I take a look at that, my KSP is going to equal my strontium ion to the first power times my chromate ion to the first power. Okay, and I don't have a multiplier in here because it's a 1 to 1 to 1 ratio. So I plug my values in, and I see I have 0.03 of my chromate, and I see I have 0.006 of my strontium. And so my KSP then becomes 3.6 times 10 to the negative 5. That's just from my table. I can use that too. Okay, I could calculate it out that way. But be careful. This is my value from my table. If I'm going to be mixing these together, I want you to be careful here because I said that this is going to dissociate, but we're mixing these two together, aren't we? So what happens is I'm going to be doubling the volume of things. I'm going to double the volume, and let's just assume, let's make an assumption here because it doesn't really say. Let's assume equal amounts are going to be mixing. Equal volumes are mixed. So if we do that, that means that it actually takes and splits my molarity in half. That will give me a half number of moles with that. So my strontium actually, in this case, is going to end up being 0.006 divided by 2, and that gives me 0.0030 molar solution. And my chromate, CrO4 negative 2, is going to do the same. 0.003 divided by 2 gives me a 0.0015. Okay, so really I can look up this value from the table, but I'm going to be using, when I do my Q, I'm going to be taking a look at this. I see that my KSP is going to equal my strontium times my chromate. That will equal 3.6 times 10 to the negative 5. But if I take a look at my Q, while it's going on, I take, let's see, I am taking my 0.003 from here, and I'm going to be multiplying that by my 0.0015. And so my QSP is going to be 4.5 times 10 to the negative 6. Okay, so what does that mean? Who's bigger? When I see my KSP, I see that I have 3.6 times 10 to the negative 5, and I see 4.5 times 10 to the negative 6. My Q value is less than my K value, so no precipitate. Okay? So that's all we have to do. 4.5 is definitely going to be small. Times 10 to the negative 6 is definitely smaller than anything times 10 to the negative 5. Okay, so we account for, when we mix them together, the volumes of things. Okay, we're going to form 0.2 liters of a solution of one thing and mix it with zero point 0.8 liters of another. Now we don't assume any of those. So I'm going to be mixing K2CrO4 plus strontium nitrate, and I'm going to be getting strontium chromate, and that's going to be potentially my solid, and I'm going to get potassium nitrate. And we don't really care about that guy. This guy is the one that we're tracking. That's going to be the insoluble one. Notice that I started with 0.040 molar solution, and I'm adding 0.800 liters of it. And I have here 0.0060 molar solution, and I'm adding 0.200 liters of it. Okay, so when I do this, I'm going to be forming strontium chromate. Strontium chromate is CrO4, but that's going to dissociate into strontium ions. And I shouldn't have a double arrow there because it's going to be forming potentially a precipitate with it. That'll form a solid, and so it's stuck. And so that's going to be one of those. And then I have one chromate in there, CrO4, -2. And again, that's to the 1 power. Okay, now using my table, I see that this value is going to be 3.6 times 10 to the -5. Okay, my strontium chromate is actually on the table. Now, if I take a look at my values, well, I see if I have these in here, this ends up being my Q value ends up being 0.002 or 0.012, and how I got that was, well, I have 0.006 divided, or I have 0.2 liters, but how much did I have total? Well, I have 0.0060 moles for every 1 liter, and how many liters did I have in here? I had 0.2, okay? And so I'm going to be adding in there 0.0012 moles of the solution, okay? And since it's a 1-to-1 ratio, I don't have to worry about that. And then the other one, we saw that I have a 0.040. That's per liter, but I have 0.8 liters that I'm going to be adding. And so what does that end up being? That ends up being 0.032. And so if I multiply those together, I get 3.8 times 10 to the -5. It's pretty close, guys, but my Q value actually is larger than my K, and so therefore a precipitate is formed. Okay? So again, you just take a look at the tables and do it that way. All right. Now, moving on to the next scenario, we're taking a look at water solubility. And one way to establish that is between a slightly soluble is to stir the solid in there to form a saturated solution. Solubility of the solid, we'll just call it S, in moles per liter is related to the solubility product. Okay, remember that's at the end of the equilibrium. So if we stir it up, let it settle out and everything, we see that I'm going to get barium sulfate. That's a solid. And that will dissociate into my barium ions plus my sulfate ions. So my KSP value is going to be 1 barium times 1 sulfate. Okay, and again, that's because it's a 1-to-1-to-1 ratio. So looking at my table, I see that barium sulfate has a 1.5 times 10 to the -9. Again, that comes from the table. I didn't have to do any calculation from that. 1.5 times 10 to the -9, that will equal x squared. So x ends up being 3.99 times 10 to the -5. Okay, so that's just going to be my KSP, that's my X value of how much is going to be there in terms of the barium sulfate. Okay, now what we're going to do with that is then calculate that solubility in moles per liter. Okay, so what we do is this. Okay, we started with barium fluoride now. Okay, that's going to be dissociating. We have barium and we have 2 fluorines. Okay, I found my KSP is going to be equal to my barium. There's only one of those times Remember, this is one of these, so we're doubling my fluoride, and it's going squared. And so looking up barium fluoride on the table, I see 2.4 times 10 to the negative 5. That's just, again, just from the table, is going to equal x times my 2x squared. Okay, so 2.4 times 10 to the negative 5 is going to equal 4x cubed. X then is going to equal 1.82 times 10 to the negative 2. Now, to this point, we've just given numbers, guys. What that number means is that's how many moles per liter that you would need that's its solubility. That's how many you can put in. Okay, so again, 1.82 times 10 to the negative second. I've never mentioned this before until this point. We have that many moles per liter. Okay, now the next part of this is saying, well, okay, moles, but we don't usually measure in that. What if it's grams per liter? Because that's usually the more functional part of chemistry. Well, remember, we started with 1.82 times, 1.82, clean this up a little bit, times 10 to the negative second moles of barium fluoride per liter, okay? And this is asking now in grams per liter. So 1 mole of barium fluoride, we know how to do this. This is just simple mole calculation. I look on the periodic table, I see I've got 175 grams per mole. And that's going to equal 3.19 grams of barium fluoride per 1 liter. Okay, so that's all I do for that type of calculation. Okay, that I can put in 175 grams of barium fluoride for every liter of solution, and that will still be able to dissolve. That's how many I can put in. Now, taking a look at the solubility of barium sulfate by itself. Now, that's the one, remember, I'm just going to keep that in there. That was 3.99 times 10 to the negative 5. We did that one. But let's now add. Okay, I'll just put that one when it's by itself. We saw this to be 3.99 times 10 to the negative 5. That was from example 8. Okay, so we calculated that out to be. Now, we're going to add in a little bit of extra sulfate in there. So notice my KSP is going to be barium times my sulfate. And we saw that to be 1.59 times 10 to the negative 5 equals my x times my x. And that's going to be my sulfate. And these are all to the first power. Okay, that's with my barium sulfate. Now let's take a look at my sodium sulfate. Now notice with sodium sulfate, that is a 2 sodiums plus 1 sulfate in there. So I'm going to be adding in KSP is going to be 2 of my sodiums, 2 times my sodium squared times my sulfate. And I only had 1 of those. Okay, now I take a look at that value and 1.59 times 10 to the negative 5 was equal to, if I take a look at this, well, I have 2 times 0.1, so that's 0.2 squared times my 0.1, okay, again, 0.1, and that's to the first power, and so that I see my 1.59 times 10 to the negative 5 equals my x for my barium times, now here comes my sulfate. My sulfate was 0.1 from this one, and what's my sulfate up here? My sulfate up here is x plus x. Now again, I'm making barium sulfate, so those are all to the first power. So 1.59 times 10 to the negative 5 equals 0.1x. X equals 1.59 times 10 to the negative 4. That's moles per liter, and I've just figured out the solubility when I've added in some extra sodium sulfate to it. Okay, now we're just about done. I know this is a really long section. One way to separate the two cations in the water is to add an anion. That would actually precipitate out one of the cations, and will selectively precipitate this. So some of these are just kind of a thought question. We have a solution with magnesium and sodium ions. This would be an example like trying to get hard water and soften it, so a water softener. What would be needed to remove the ions from solution? Well, one of the problems is sodium is pretty much soluble in anything. So we're going to be pulling out the magnesium. If I add something to precipitate out the magnesium, well, I could do a lot of different things. I could add in, if I add in something like sodium hydroxide. I already have sodium ions in there, so let's throw in some sodium hydroxide, and that will precipitate out. That'll precipitate out your magnesium hydroxide ions. Okay, that'll make magnesium hydroxide as a solid, as a precipitate. Now, what's going to happen is I'm going to have a whole bunch of sodium ions just kind of floating around in solution. Okay, and so then all I'll do is I'll evaporate, and that sodium will just crystallize as a salt. And it'll crystallize as like a sodium chloride or some other kind of salt in there. So again, I find something that is going to precipitate this out, and then this guy is going to be there. The problem, sodium just doesn't like to precipitate. It's very, very hard to do that, so find something for the other one, okay? Now we can use this to our advantage to do some basic math with it as well. A solution has a certain amount of this and barium ions in there, and you'd like to precipitate them using some carbonate, okay? Using the information provided, which one is going to precipitate first. So we're going to do these simultaneously, guys. Okay, we're going to do these simultaneously. This becomes almost like a limiting reagent problem. I have my barium carbonate, and that's going to dissociate into barium ions as well as my carbonate ions. Similarly, I have magnesium carbonate, and that's going to dissociate into magnesium and carbonate. And so my KSP for this side, notice this is a 1 to 1 to 1, so that's going to be magnesium times my carbonate. And so I look up these values, or I've got the values actually provided in the problem. 6.8 times 10 to the negative 6, that will equal 0.1, because I'm given the concentration with my magnesium as well as my barium. So my magnesium is there, and my carbonate, I really don't, that's the unknown, so I'll just leave it as carbonate so I know what I'm solving for. Now let's do the same thing. Before I finish anything up on this side, my KSP for this side is also a 1 to 1 ratio, and so I'm going to be seeing that my KSP is going to be barium ions times my carbonate ions. Okay, again to the first power. So this value is a 2.6 times 10 to the negative 9, and that's going to equal my 0.1 to the first power times my carbonate ion on this side. Okay, the question is, which ion will precipitate first? Okay, so now I find that my carbonate on this side is going to be 2.6 times 10 to the negative 9 over 0.1, which equals, which equals 2.6 times 10 to the negative 8. And on this side, my carbonate is going to be 6.8 times 10 to the negative 6 divided by 0.1, and that's going to equal 6.8 times 10 to the negative 5. Okay, so what does this mean? I have 2.6 times 10 to the negative 8. I have 6.8 times 10 to the negative 5. Well, that means that my barium is going to precipitate out first. The reason is this is smaller. Okay, so what that means is my barium is going to precipitate first. Okay, since it's a smaller carbonate, because I have a smaller carbonate concentration here. Okay, so that's all I do, and what concentrations I've just solved for that. Okay, the concentrations are going to be right here, and that's what I've solved for. So nice and easy. We just kind of keep track, solve them simultaneously is the key to this. All right, let's do one more, and this will be it because I want to show you one more permutation to this. A flask has, we have chloride ions and chromate ions, and we're going to add some silver nitrate to it. Okay, we want to know what's going to precipitate first, and then this time we want to know our percents. Okay, so remember what we do. Okay, first step, keep it nice and clean. Let's go two separate equations going on. I'm going to have silver chloride. That's going to be my solid. That's going to dissociate into my silver ion as well as my chloride ion. Okay, so my KSP on this side is going to be 1 silver times 1 chloride. Again, it's a 1-to-1 ratio. Okay, and this one I can actually look up on the table provided. 1.6 times 10 to the negative 10. That's again from our table. That's going to equal my silver ion times 0.1. Okay, and because I've got 0.1 there. Now, before I move on, let's do the exact same thing, and I have silver chromate this time. Now, be careful, because this is silver chromate, that's Ag2CrO4. That's my solid, so I'm going to get 2 silver ions on this. And I've got chromate, and so now my KSP is going to be 2 times my silver ion squared times my chromate. And that's to the first power. So again, looking that up, I see 9.0 times 10 to the negative 12 is going to be 2 silver squared times 0.01. Okay, and the 0.01 is going to be right from here. Okay, so now I've got this all set and ready to go. If I solve for my unknown in this case, well, I have, remember, let's get the 2 silvers by themselves. So it's 2 silvers, and that squared is going to equal 9.0 times 10 to the negative 12 over 0.01. So getting just the silver, Ag plus squared equals 2.25 times 10 to the negative 11. So my silver ion, taking the square root of that, ends up being 4.74 times 10 to the negative 6. Now let's go to this side. I see my silver on this side, and it's only times to the 1 power, okay, and it's not doubled. Okay, so looking on this side, I see that this is going to equal 1.6 times 10 to the negative 10 divided by 0.1. And so my silver in this case, Ag plus, in this case is going to be 1.6 times 10 to the negative 9. Okay, so what do we do with that? Okay, what this means is this is my smaller number. This is times 10 to the negative 9. So that means that this one is going to be precipitating out first. What was I working with? My chloride precipitates first. Because it's giving me a smaller silver value, okay, a smaller silver value means I run out of this, I precipitate this one out first. Okay, so let's take a look at how to analyze this last part, and this is going to be the last one. What is the percentage then? Okay, so let's take a look at what happens. I'm going to see 1.6 times 10 to the negative 10. That's my value. That's going to be my silver chloride. That's precipitating out. And now I plug in values. So 1.6 times 10 to the negative 10. Now the question is, which value do I use? Okay, well, I'm going to use my second value to precipitate. Use the second value to precipitate that out. I have more of that, so 4.74 times 10 to the negative 6 times my chloride. That will equal, that will give me, I should say, my chloride is then going to be 3.38 times 10 to the negative 5. Okay, so how do I figure out now? And the question is, why did I use that second one? Well, we want to figure out a percentage. Okay, so what I do now is I take a look and use my first precipitate value. Okay, my first precipitate value for chloride was my 0.1. Okay, so I take my 0.1 and I subtract off the 3.38 times 10 to the negative fifth. Okay? And so then I divide that by what I started with. Okay, so the difference in that, I multiply that by 100%, and I'm going to get a 99.97% of the first ion has been precipitated out. So I just take a look at those things, and it says, it tells me the first ion in there, so keep track of those things. And that's how much is gone, or how much is precipitated, I should say, when the second anion starts to precipitate. So just keep track of the first one to precipitate out, and then the second one, okay? And then we should be good to go. And I don't think you'll have any problems if you just keep track of who precipitates out first, and then what do we do with it to find our percentages. Whew. Good job, guys. This is a tough one, so good luck with some of the problems, and this is a good review for previous sections